Good afternoon. My name is Bryce Kellogg, and today I'm going to be talking to you about ultra-low power gesture recognition. This is work I did with Vamsi, Talla and my advisor, Gollakota. Now, increasingly, we're seeing new forms of user interaction that go beyond the traditional mouse and keyboard. And we're all familiar with the Kinect and how it has enabled gestures as a way of interaction between humans and machines. Unfortunately, there are a couple limitations with Kinect. First, it's limited to line of sight, so you really need to be right in front of it for it to work, and there can't be anything in between. And second, it requires significant amounts of power, so it's infeasible on battery-operated devices. And so, in this project, we wanted to address these two limitations. We want to enable the same type of gesture interface on any device, no matter how power constrained, and also have it work in non-line of sight. So can we not only have our system work on a power-hungry Kinect, but also on Internet of Things devices such as thermostats or other sensors that are increasingly being used in the home? And we also want to enable always-on gesture recognition on smartphones, where the phone can be in your pocket and the user can control it with simple gestures like we're going to see here. So note that nothing I've shown you so far was possible using existing technologies. So how do we achieve the above functionalities? Our high-level idea is to leverage changes in ambient wireless signals that are all around us. See, as you sit in this room, there are so many signals, including Wi-Fi, cellular, and TV transmissions. And as you perform a gesture, the human body creates minute changes in these signals that we can detect. Additionally, since wireless signals work in non-line of sight, this opens up new scenarios for gesture recognition, such as silencing a phone call without taking my phone out of my pocket, or maybe skipping a song while you're jogging without having to look down and fiddle with your phone. And to this end, we introduced AllSee. AllSee is the first gesture recognition system that can run entirely without batteries. Our prototype, you can see it right here, leverages ambient TV and RFID signals. AllSee consumes orders of magnitude less power than a traditional gesture recognition system. And we even integrated it with a mobile phone and showed that it works even when the phone is in your pocket. So let's see how AllSee works in practice. Let's take a look at our hardware architecture. The architecture consists of a few basic components. You can see we have a single antenna, which we tune to the frequency of interest. Second, we have an ultra-low power wireless receiver, which converts radio waves and the changes caused by a gesture into a signal suitable for processing. And then we have a digital logic block that samples this signal and performs gesture recognition and detection. And then since our prototype is battery-free, we also use an RF energy harvester that can harvest energy from TV and RFID signals, and in general can provide us with about 40 microwatts of power, depending on how far we are from the RF source. Now, getting all these components working together into an operational system requires that we have our wireless receiver and the digital logic block work together within this power constraint of 40 microwatts. So let's see how AllSee achieves that. Let's start with the wireless receiver. Now, traditional radios consume significant amounts of power. They have components such as oscillators, PLLs, amplifiers, high-speed ADCs, and all of these consume orders of magnitude more power than we have available from our harvester. So this brings us to our first challenge. How do we access these changes in wireless signals without incurring the power drain of a traditional radio? Our solution is to leverage the Ambient Backscatter receiver that our group introduced last year at SIGCOM. And this is an entirely passive receiver. It has none of those active components that I just mentioned. It consists entirely of a couple resistors, a couple capacitors, and some diodes. And the circuit acts essentially as an envelope detector and low-pass filter. So you can see we get the raw signal from the antenna port, and what it does is it removes the carrier frequency and any high-speed changing signal from, for example, TV transmissions. And what we get at the output is just the amplitude. And using this style of receiver, we can cut down our power consumption to 0. It's completely passive. This is significantly less than the traditional radio. Now, if we go back to our architecture, we know that our wireless receiver consumes 0 power, which is well within our power budget of 40 microwatts. And so let's move on to the second part, which is the digital logic. So designing a low power classifier is challenging for 2 main reasons. One is that our receiver, if you remember, only provides amplitude information. There is no phase information. And this can be problematic because prior solutions use techniques such as music or Doppler or angle of arrival, all of which require the phase information, which we don't have. And second, and maybe more importantly, is because our prototype here is completely battery free, we can't run computationally intensive operations on it. We're limited to really simple adds, shifts, maybe comparisons, definitely no machine learning or really even multiplication. So let's take a look at the first challenge here. How do we map gestures to amplitude-only signal changes? So our solution is to build up an amplitude library of gesture primitives. So let's look at an example of 2 of our primitives, which is a push gesture and a pull gesture. And the high-level idea is that each gesture primitive maps to a unique waveform in the underlying signal. For example, if I perform a push gesture, as my hand moves towards the receiver, this is the signal we see. Alternatively, if I perform a pull gesture, we see a slightly different signal. Notice the general increasing trend in the push and the general decreasing trend in the pull. This is caused by the fact that when my hand is far away from the receiver, any reflections are going to be picked up weakly by the receiver when my hand is far away. And when my hand is close by, we're going to get much stronger reflections. And this explains the small to big and big to small trend that we're seeing here. So let's take a look at it live. This is the demo that you were promised. So what we have here, let's hook up our webcam. So we got here, this is our prototype. And you can see it's hooked up to an oscilloscope, which we're showing just the output of the envelope detector. And you can see as I move my hand, right, we see signal changes. So if I perform a push followed by a pull, you can see the general increasing trend in the first part and the general decreasing trend in the second part. And this is how we tell the difference between a push and a pull. Okay? So now let's go back to the slides here. Full screen. And so we can generalize this beyond just a push and a pull to more gestures. And we can see here, these are the 8 gestures that we evaluated, including a flick gesture, a zoom in gesture, a zoom out gesture. And you can see that each one corresponds to a unique signal waveform. And we can classify these using only add, shift, and compare operations. Very simple operations. And while this is great, this doesn't really solve our problem because these operations can still be extremely power hungry. For our digital logic, we used an MSP 430 microcontroller, which is one of the most power efficient microcontrollers on the market. And in active mode, it can still consume a milliwatt of power, which is way too much for our energy harvester. So what we need is some type of workflow that allows us to sleep most of the time and then only wake up periodically to sample and perform a little bit of computation. So we broke this workflow into 4 steps, 4 modes. We have sleep, which is the most power efficient. It consumes about half a microwatt of power. We have sampling, where we wake up and we sample with a low-power ADC. And then we have detection, where we perform some minimal computation, and then finally classification. So let's see how these all fit together. We start out, as the signal comes in, sleeping most of the time, which is represented by our little blue blocks down there. And then we wake up at about 200 hertz to sample. And once we detect the start of a gesture, which is seen by sudden increases in fast changing of the signal, we start detection, where we gather a little bit more information about the gesture, mainly doing stuff like peak detection. And then finally, once the gesture is over, we run classification once, output the result, and go back to just sampling and sleeping. And using these techniques, we can bring the power consumption of our system down to 30 microwatts. And this is well within our power budget of 40 microwatts. And then we're also able to get the response time down to 80 microseconds. So this is all happening in real time. So now that we know how AllSee works, let's look at how well it works. So the first thing to ask about is classification accuracy. So we asked 5 participants to perform our 8 gestures, each gesture 20 times, for a total of 800 gestures. Pretty sure that adds up. And what we saw was that 0.25% of these gestures were not detected. That's 2 out of our 800. And then we saw that 94% were correctly classified. And I'd like to point out that this was done using those very simple operations I mentioned earlier. They're user-independent, hard-coded rules. And if we were to have a little bit more extra computational power available to us, for example, on like a smartphone or something like that, then we could bump this up significantly closer to 100%. So the next big question is false positives. Since what we're doing here is we're detecting human motion, it's natural to ask, how does random human motion affect it? So what we did was we set up our prototype here in an office space shared by about 12 people. And we measured the gesture output over 24 hours. And here's what we saw. So it fluctuated wildly. You can see most of it during lunchtime when people are walking back and forth. And this averages out to about 11 false positives per hour. Now, to reduce this, what we did was we implemented a start gesture. So in order to go into actual gesture detection mode, you flick twice at the device. And this reduced false positives significantly, as you can see by the green line, to 0.083 per hour. Much less than before. So now, having done all this evaluation, we want to see AllSee in action, in the real world. So we hooked it up to a phone. We reduced the form factor to fit in much nicer with a phone. And we even 3D printed a case so we could stick it on there, plugged it in with USB, and we tested how well it worked inside the pocket. So performing gestures through the fabric of your clothing. And what we saw was it works about 90% accuracy. And you'll notice this is less than the 94% outside of the pocket, but this is for all 8 of our gestures, and we think it's sort of a more realistic scenario when if you would integrate this into a product, you'd probably cut down from 8 gestures to like 3 or 4 that are very specific to some scenario. And this would allow us to bump up the accuracy significantly. So to conclude, AllSee is the first gesture recognition system that can run completely without batteries. We leverage ambient TV and RFID signals, and it consumes orders of magnitude less power than any other gesture recognition system out there. Thank you. Any questions?
This is great work. I'm curious about how sensitive your results are to distance and timing.
Yeah.
timing of your gesture, as well as orientation?
Yeah, so we evaluated some of those in the paper, and what we saw was the distance, it works up to about 2.5 feet from the user from the device, and it's not really dependent on distance from the device to any RF source.
Okay.
And as for orientation, that's really a function of the antenna. So what we used here was just a normal dipole antenna, which has dead zones on the edges. So that's going to affect how orientation affects it.
But the amplitude would change depending on the orientation, right?
Yes.
So in that sense, it'll affect.
In that sense, you can calibrate it. We normalize it, the signal also. So you can calibrate it in various ways. Anything else?
So, yeah. Let me
keep going.
Let me keep going. I'm curious about also the library of gestures.
Yes.
That it will generalize to. I mean, so fine-grained gestures may be difficult, I suppose. And if I wonder if you picked these gestures because they were somehow more detectable, more separable in terms of some distance metric, or why these 8? And
well, so these 8 were and you're right, they are more easily able to detect than certain other gestures like swipes, for example. But these were the most useful gestures that we saw that also mapped to fairly clear waveforms. But you're right, there are some that don't map quite as easily.
Thank you.
Thank you.
Hi, I wanted to know about that 40 microwatts.
40 yeah.
How harvestable is it outside of urban areas? Like if I'm in the mountains and there's no RF sources?
Yeah.
Do you have any idea?
Well, so for RF harvesting, you obviously need some type of source, right? And TV tends to be pretty ubiquitous. There are certain places where TV doesn't work if you're, in your basement, for example. But we're also looking at extending it to other signals besides just TV and RFID, cellular and Wi-Fi, for example. And oftentimes, the scenarios that you're looking at, for example, silencing a phone call, if we're doing this with cellular signals, then you already know you have a signal. So for lots of scenarios, you already know there's some type of signal you can use. But if you're in the mountains, I don't know.
Hi, nice work. I'm curious about did you guys use the analog to digital conversion to get the
Yes.
digital value from the amplitude?
Yes.
So basically, I'm curious about your sampling rate, 200 Hertz. It seems that the ADC is usually the most power-consuming module in terms of the microcontroller. So do you have any tricks to tune this frequency to sampling frequency to 200 Hertz to make sure the power consumption is lower than your energy harvesting budget? And also, I'm thinking about maybe the sampling frequency will determine the frequency of your gesture, right? Cannot be very fast.
Yeah.
Yeah.
So in general, your human movement tends to be fairly slow. Like I'm not going to be, trying really hard to do really fast gestures. I'm going to strain my arm doing that or something. And we found that 200 Hertz works pretty well for sort of a middle ground between giving us enough information and sort of low power modes. And we also evaluated different sampling frequencies, and we saw that we could go down to about, I think, 100 Hertz before we started losing accuracy. So you can definitely play around with the sampling frequency to optimize for power or other things. Any other questions? Okay. Thank you.
Well, I have just one quick question just before you go away. Just to, maybe you could just comment a little bit on future work. Just to tell us what you think is the most important way to extend this work in the short term and why.
Okay. I think the most important way to extend this is sort of integrating it into real devices. So right now we've got a little PCB, and we're working on integrating it into phones and stuff like that, sort of off-the-shelf hardware, to try to make it work with more types of signals and more devices.
Okay, great. Thanks very much. Let's thank Bryce.
Thank you.